It's been shown that early diagnosis greatly improve the odds of recovery from an illness. Sometimes symptoms like an irregular heartbeat don't show up when you're visiting the doctor. So it's very important that we're able to monitor health remotely and continuously. Now, sensors are getting better and better at providing us with reliable and informative data, but there's still a major challenge we have to address, and that is power. How do we power these kinds of devices for long periods of time? Because every time that a device needs to be removed and recharged, it's an opportunity for data to be lost. And it doesn't just stop with these advanced monitoring solutions. Because if you look at the impact that Hurricane Maria had in Puerto Rico and that wildfires are having in California right now, power is not necessarily a guarantee. So we need to be thinking about ways to keep our devices up and running when we're away from the electrical grid, especially if you have a health concern. So over at the Thesis Center, I've been working on a project where we capture body heat and convert that into usable electrical energy. We use thermoelectric generators, which are special ceramic materials designed to produce electricity whenever they're exposed to a temperature difference, or a hot side and a cold side. These are already used in industrial systems. They're working with very large components at very high temperatures, and they're made up of rigid metals and ceramics. They're not things you want to carry around with you all day. So to capture body heat, we need to be smarter. We want devices that are robust and comfortable to wear for long periods of time, and they're very efficient because they don't have a large temperature difference to work with. It's just a small gap. So we start by stripping away the rigid components, the plates and everything, and strip it down to just the thermoelectric bits that we need. Then we encase all this in soft silicone rubbers. But the trickiest part is how do you wire all this together? And that's what my research is all focused on, is developing inherently soft circuitry. Because if you want devices that can move and behave like your skin, you need materials that can do that. And so traditional wiring like copper wire isn't going to work because the skin is a little odd that it can not only bend and flex, but it can stretch. So copper wire, if you try to stretch it, it's just going to snap. So we turn to liquid metals. These are alloys that are very low melting points. It means they're liquids at room temperature. They can flow through a channel or stretch out without breaking or losing conductivity. We can pattern these metals in two different ways. One of them is with 3D printing. This allows us to directly write out circuitry right onto any surface that we want. This is really useful for generating pathways with very specific geometries and high resolution. The other option is to use a spray deposition process. And this can be thought of as basically spray painting metal through a stencil to generate your circuit. Both of these techniques let us make devices that are conformal to the skin and follow your motion naturally. It can keep our devices up and running without being tied to the electrical grid because our bodies can be the batteries. Thanks.